Hey everybody. Today we're going to start integrating e to the x. We know how to differentiate e to the x. It's super simple. The derivative of e to the x is just e to the x. Flipping that around, we get a rule for the indefinite integral of e to the x dx. It's just e to the x plus c. The most general antiderivative of e to the x is e to the x plus c. We can do a lot of integrals just using some reverse thinking. For example, the integral of e to the 1/2 x dx. I need to find a function whose derivative is e to the 1/2 x. So just based on my knowledge of the derivatives of exponential functions, I know I'm going to have something like e to the 1/2 x here. However, that answer will be off by a factor of 1/2 because if I differentiate e to the 1/2 x, I get a factor of 1/2 in front. I want to kill that, so I'm going to include a factor of 2 in my most general antiderivative. If I differentiate this function on the right, 2e to the 1/2 x plus c, I get e to the 1/2 x dx back. You can get through a lot of integrals just using that sort of backwards thinking. Let's look at a couple that are a little more complicated where we might actually want to use a more sophisticated technique. Example 1, e to the 5x secant squared of e to the 5x dx. This is a good one to use a u-substitution on. We have an inside function, e to the 5x, and its derivative appears as a factor in this integrand, at least up to a constant multiple. We set u equal to that inside function, e to the 5x, differentiate, and then solve for dx. dx equals dx equals du over 5e to the 5x. Now we substitute into our original integral. We take out the inside function and replace it with u equal e to the 5x. And we take out our dx and replace it with what that's equal to, du over 5e to the 5x. There's some cancellation now. I factor out the 1/5. I have 1/5 integral of secant squared u du. Now we're happy. We have a anti-differentiation formula for secant squared of u. We know that the derivative of tangent u is secant squared u. So the antiderivative of secant squared u is tangent u. Finally, let's take out the u and put back in the function of x that it's equal to. Our final answer is 1/5 tangent of e to the 5x plus c. Example 2. Integral from 2 to 3, e to the 1 over x squared dx. This time it's a definite integral. We don't let that bother us. We just go ahead and get an antiderivative and then plug in those limits of integration at the very end. This one's going to want another u-substitution. We have this inside function, 1 over x. It's inside the exponential function. And its derivative is a factor in this integral. The derivative of 1 over x, the derivative of x to the negative 1, is going to be something like 1 over x squared. Let's see the details. U equals x to the negative 1. Differentiate to get negative x to the negative 2nd. And solve for dx. We get negative x squared du. Now, I'm going to take out the inside function 1 over x and replace it with u. Take out the dx and replace it with what it's equal to, negative x squared du. And cancel out the x squareds. Notice that I wrote x equals 2 and x equals 3 for the limits of integration. I want to keep straight that those are x values, not u values. When I substitute in after anti-differentiating, I want to make sure I plug those in for x, never for u. The antiderivative here is super easy. When I anti-differentiate e to the u, I just get e to the u. Before I plug in the limits of integration, I take out the u and replace it with 1 over x. And then finally, plug in x equals 3 and x equals 2 to get the answer. E to the 1/2 minus e to the 1/3.